Mr. McBrien. This is SCH4U, Introduction to Thermochemistry. So the Ontario curriculum would like for us to be able to talk about chemical processes based on energy changes and to essentially be able to discuss them in terms of efficiency, in terms of their significance around physical and chemical implications. So let's talk about a few examples of where thermochemistry can give us insights. So we might want to ask ourselves how fast a glacier might recede this summer. We might want to evaluate one fuel versus another for purposes of a given application. A common challenge in chemical engineering is the idea of taking a reaction that works well on a small scale and coming up with a way to safely activate it on a large scale. And obviously, this isn't something I need to worry about, but we might want to ask ourselves, how many sit-ups do we need to do in order to burn off that Big Mac we had for lunch? Okay, so in order to gain some insights on those kinds of things, first we have to do the usual thing from the introduction to any unit. Talk about some definitions and things like this. So thermochemistry is the study of heat change in chemical reactions. And from that perspective then, we start to talk about energy. And energy from our perspective then will be the capacity to do work. Thermal energy, defined as the energy associated with the random motion of atoms and molecules. Chemical energy, energy stored in the bonds of chemical substances. We talked a lot about that in the organic chemistry unit. Nuclear energy is energy stored within the neutrons and protons in the atom and the way they're put together. Electrical energy, more a subject for physics for the most part, is the energy associated with the flow of electrons. And potential energy is energy available by virtue of an object's position or composition. So when it comes to energy changes in chemical reactions, our key focus for this unit, we need some definitions of some things that words we've known since before kindergarten, right? So from this perspective, heat will be defined as the transfer of thermal energy between two bodies at different temperatures. Temperature is a measure of thermal energy, but it's not exactly thermal energy. Thermal energy has a different definition. It's the total quantity of kinetic and potential energy in a substance. And so temperature isn't thermal energy. They're not the same thing. And to gain a perspective on this, we can consider a hot cup of coffee and compare that with a much larger but cooler bathtub filled with water at 40 degrees. In fact, the bathtub has greater thermal energy by virtue of the fact that there's much more material there. Okay, so one other thing we need to discuss is the first law of thermodynamics. And if you've been listening, I talk about the first law a great deal. And we also think of it as the law of conservation of energy. The idea that energy can't be created or destroyed, it only changes forms. This is, in fact, a very hard theory to prove. It's very hard to prove that this is the case. But the fact of the matter is, no one's ever proven it wrong. And in fact, this theory, law, whatever you want to call it, is extremely important to thermochemistry. It underlies everything that we do, and we won't get more than a couple of slides in today to the rest of our discussion without the first law becoming incredibly important to those ideas. All right, so we need to do some other definitions as well. We need to define a system. Crazy, some of the interesting things for which we need to design definitions now, but we really need these in order to discuss transfers, and it'll become more obvious in a few minutes, I think. So we define the system as the part of the universe in which we're interested. And we're going to contrast three systems in order to get an understanding of how we'll categorize these systems in order to do our experiments in the future. So on the left-hand side, we've got an open system, and this could easily be, for example, a Coke bottle with the top off of it. Now, in an open system, material doesn't have to be water vapor. Material can move in and out of the system without a problem. Heat, of course, can move in and out as well. This is what we call an open system. And in many ways, it's not very interesting for us because it's so hard to control what goes on with the movement of these things. So, when it comes to an open system, then, we can exchange mass and energy with the rest of the universe. Now, a closed system is much more interesting for our purposes. So we can think of this as being that Coke bottle, but with the cap screwed on. And in this case, while the system can exchange energy, heat, with the outside world, there's no capacity for mass to move back and forth. It's a sealed system. And then we have what's called an isolated system. And this one is extremely interesting from a thermochemistry point of view, and rather hard to implement. So in an isolated system, heat can't get in or out, and neither can mass. And so this system is completely isolated from the outside universe, and we can gain some valuable insights into processes if we can design a system that can closely match this. And we'll do our best. So we might think of this one, rather than being the Coke bottle, this might be a good vacuum thermos that can hold coffee hot for a very long time. The reason it can hold that coffee hot for a long time is because there's very little heat that can move in or out of the system, and it's sealed tight so no water vapor or air can get out of it as well. So those are three systems, and you're going to need to memorize these and understand the implications of each one in terms of the questions that we're going to try to answer over the course of this unit. So next, we'd like to define a couple of processes. And these are processes mainly with which you're already familiar, but we're going to categorize them carefully now such that we can gain a better understanding of our universe by observing these. So an exothermic process is a process that gives off heat. So it transfers thermal energy from the system to the surroundings by virtue of the process. So in this case, we have the oxidation of hydrogen going from hydrogen gas and oxygen gas to liquid water. Now, when this occurs, we also call this combustion. There's a great deal of energy produced, and that's what we're seeing here. And that is a perfect model of an exothermic process. But there are other exothermic processes that aren't quite so intuitive. So when we take gaseous water vapor, and we condense it to liquid form, energy is inherently produced. So we're extracting energy, or energy is produced and given up to the universe as this happens. So this is another exothermic process, and not quite so obvious as the other. Now, as usual, of course, whenever we have a push, we have a pull. So an endothermic process is a process in which heat has to be supplied to the system from the surroundings. So it's the opposite direction. So we might have a kind of classic endothermic process like taking mercury oxide and chasing off oxygen by putting heat in. So mercury oxide goes to liquid mercury plus oxygen gas, and we have to put energy in to achieve this reaction. Or we might take solid water and turn it into liquid water. And in order to do this, the universe has to supply energy to the process. So what might we observe that? Well, we might observe that by you dropping an ice cube into a glass of Coke, and the energy, the thermal energy from the Coke, is transferred to the water in order to melt the ice cube, and your drink gets colder. Now, while we're on the subject of exothermic reactions, let's quickly talk about nuclear energy in order to get at least a context for some of the things we'll discuss later. So all nuclear reactions are exothermic. And one thing worth noting is that there is far more energy tied up in the nucleus of an atom than there ever is in the bonds between atoms. And so for this reason, there's far more nuclear energy available per unit mass than there is chemical energy. There's two main types of reactions we'll consider: fusion and fission. Fusion, no great shock, is the combination of two different atoms combining together to form a larger element or larger elements. So in this case, we have two isotopes of hydrogen combining to form helium and giving off one neutron. In fission, we have a situation of, instead of putting small atoms together, we have large nuclei and we break them apart. So here's an example. Here we can bombard uranium with neutrons and produce two smaller atoms, krypton and barium, and three neutrons, as well as a very large amount of energy. And so this gives us a good perspective of why nuclear reactions proceed so well. We put one neutron in, we get three back out, so this reaction can proceed very quickly once it gets started. So back to the idea of heat. What I'd like for us to do is to cover one of the concepts, a very important concept in thermochemistry, and to do it in a kind of a unique way. What I'd like us to do is do a little thought experiment and think about, put ourselves in the shoes of chemists back 200 years ago and try to think about the universe and actually intuitively derive an equation for heat capacity. So let's see how this goes. So for starters, let's just consider a really simple problem that we don't think about very often, but that is at the core of this heat capacity idea. So imagine that the sun's shining down on one of these covers for access below the street. And imagine that the sun is shining on that piece of steel. So what happens? Well, if you've ever walked around in bare feet, you know that it gets quite warm. So why? Well, the answer to that is that energy is coming down from the sun. It's hitting the earth in a given area at a fairly constant amount of energy per square meter. And we've got perhaps 2/3 of a square meter of person-hole cover there, and it's collecting energy from the sun. Now it heats up as the sun hits it. Let's say that there's a break in the clouds and the sun begins to hit it. It begins to heat up, right? What would be the difference if it were half as thick? So instead of, let's say, 2 centimeters thick, it were 1 centimeter thick. What would be the difference? Think about that and think about why that is. Now, the second part of this problem is, what if it were aluminum? And what if aluminum absorbed the same amount of energy per second of sunlight? Would it heat up faster, slower? And why? Okay, so we're going to actually ask ourselves this and derive expressions for it, which we could then go and test experimentally if we wanted to. So we're going to actually attempt to derive the equation for energy required to heat a substance now. And in fact, what I'd like you to do is pause the movie and try it yourself. Try to ask yourself what is important and how you might come up with an expression for how much energy it takes to heat something up. Whether it's that person hole cover or whether it's a cup of coffee, just go ahead and sit down take say 5 minutes and mess around and try to come up with what you think might be a reasonable expression for this. When you're finished, when you're ready, unpause the movie and I'll take a step by step through this derivation. Okay, welcome back. So in order to create an expression for this, it's as easy as anything to just take things stepwise and ask ourselves what intuitively we can expect about our situation. So we're looking for an expression that could describe how much energy it takes to heat up, let's say, 1 kilogram of water. Well, the first thing we would ask ourselves is the mass important? So the question, will it take the same amount of energy to heat a large object as a small one, comes to mind, right? So if we have a glass of water at 3 degrees Celsius or a swimming pool at 3 degrees Celsius, which one would take more energy? Or would they require the same? Well, I think you probably have already said, well, it's going to take more energy to heat up a swimming pool than a glass of water. And in fact, we can speculate, before we do any experiments, we can speculate that the amount of energy required then is going to be proportional to the mass. Whether it's water, whether it's aluminum, it's going to be proportional to the mass of the material. Okay, so step 2, does the energy depend on the change in temperature, so the magnitude of the change? And to put that into a bit more concrete terms, if we want to heat up something 5 degrees, so if we want to heat up our glass of water from 3 degrees to 8 degrees, how will that compare to heating it from 3 degrees to 503 degrees? Does it matter? Well, we can probably speculate that the larger the change in temperature, the more energy would be required. And we could be reasonably confident. Proportional? We're not sure, but of course, again, we can test this based on experiment. So then the next question we might ask ourselves is, okay, is there a difference between heating up that glass of water or a glass of mercury? Or you name it, right? Is there a difference between heating up a kilogram of water or a kilogram of cat? And this is the kind of thing we can't be sure of. I don't think intuitively anyone would say, no, a kilogram of water will take more energy to heat up than a kilogram of cat. this is the kind of thing that it's logical to check with experiments. But please, to be clear, don't heat up your cat. In fact, if we were to go and design the experiments then, for example, putting two different materials in sunlight and letting them absorb the same amount of sunlight and see how much they heat up, we would find that in fact different materials require different amounts of energy. So, aluminum requires 0.9 joules per gram per degree Celsius. Iron, so we could say roughly steel, requires just under half of that amount. So in fact, it would have taken much longer for that person hole cover to heat up if it were aluminum than it would if it were iron. In fact, it would take twice as much energy. Now what's interesting here is as we do our experiments, we can see that for some reason, water requires more than 4 times as much energy per gram than aluminum, and nearly 10 times as much per gram to heat up than iron. So water has a much higher energy capacity, heat capacity, and we can talk about why that is later. But what we can say is that this value, the amount of energy it takes to heat a gram of something up per degree, is different for different compounds. Even, interestingly enough, and this gives us some insights, remember that the formula for graphite and diamond is identical. So clearly there's something to do with the bonding involved, because the atoms are exactly the same in graphite versus diamond if you have the same weight. Okay, so now we kind of have a feeling for this, right? So we have a situation where we know that we have to have a constant in there that is specific to a given material. We know that it's probably proportional to temperature, and I can say now that in fact this was verified experimentally to be the case, that it's roughly proportional to temperature as you go, and that it's proportional to the mass. So when we combine all these things together, then we get energy is equal to the mass times the heat capacity for that material times the number of degrees that you want to heat it up. Now, I'd invite you to pause the movie again and think about this question. What does the first law of thermodynamics tell us about the energy that would be released if we were to cool an object at a given number of degrees? So remember what the first law is and think about the answer to that. And when you're finished, we can move on. Now, we talked about our various systems and the implications of these with regards to interaction with the outside world. Now we're going to apply some of those concepts right now to the equation that we've just designed. So first off, a quick definition so that you'll have this handy for tests and such. The heat capacity of a substance is the amount of heat, Q, required to raise the temperature of a given quantity of the substance by 1 degree Celsius. So this is specific to the size of the item that's being warmed up. The specific heat capacity, small c, of a substance is the amount of heat Q required to raise the temperature of 1 gram of the substance by 1 degree Celsius. So this is the value that you would look up in order to do given calculations. So the heat capacity of an object, say a coffee cup or a cat, then would be the mass of that object times the specific heat capacity of the material from which it's made. And then if we want to calculate Q, we simply multiply that times delta T. So Q would be MC delta T if we have those three numbers, or if we have the heat capacity of the substance, it's just C times delta T. So if we wanted to apply this equation then to a classic problem, this kind of thing, how much energy is absorbed by 600 grams of water if you put it in the microwave and heat it from 20 degrees C to 85 degrees C? Well, then what we do is we essentially apply it. But first, let's talk a little bit about the way that we do these kinds of experiments in the lab. So calorimetry is the measurement of heat going into or out of a system for chemical or physical processes. The heat released is equal to the heat absorbed. That's our first law of thermodynamics again. The device we'll use to measure this heat absorption or release is called a calorimeter. And this is a cartoon of a calorimeter here. So what we would typically have is a known amount of water inside the calorimeter, some process that goes on inside that calorimeter, submerged below the liquid, and a stir to make sure that the heat is evenly distributed, a thermometer to monitor what's going on. So this gives us the capacity to have a closed system. We will need to make some assumptions when we're using a calorimeter. So when you're doing it, assume that energy transferred from the calorimeter to the outside environment is negligible. In other words, that it's an isolated system. Assume that the thermal energy absorbed by the calorimeter itself is negligible. Now this is an interesting one. Obviously there's a source of error there, because any object is going to have some absorption. Now you're going to make the assumption that any aqueous solutions have the same density and specific heat capacity as water. So that means 1 gram per milliliter and 4.18 joules per gram per degree Celsius. Okay, once we have these assumptions, we can do these kinds of experiments. So here's something more like what we would use in a lab. We'd use 2 layers of styrofoam in order to get pretty good isolation from the outside world. A simple wire stirrer intended to have low heat capacity. Remember, that's one of our assumptions. A thermometer and a reaction mixture. So this is our approximation of an isolated system. So no heat enters or leaves our calorimeter. And we can do experiments like the one we just talked about, asking ourselves how much heat would be absorbed heating up water. Well, we can also look at the opposite experiment. So we can pop the lid off the calorimeter and drop an 869 gram iron bar into the liquid and observe as it cools down. And if we measure its starting temperature, for example, 94 degrees Celsius, we measure the final temperature of the system, then what we have is a measure of the heat that was given off, provided we use our equation. So this is the calculation here. Remember that the specific heat capacity of iron is 0.444 joules per gram per degree Celsius. We have the mass. We have the change in temperature, right? Plug it in, and we get negative 34,000 joules. So the negative, all this indicates is that heat is being given off. And we can do similar calculations working in a calorimeter. In this case, a student takes 50 mils of water in the coffee cup calorimeter, places a sample of gold that's at 100 degrees Celsius into the calorimeter, and then measures the final temperature at 21.33 degrees C. Now, based on that, Q can be calculated. the quantity of thermal energy that's been absorbed by the water in the calorimeter. So in this case, the identity of the sample, the fact that it's gold, has no impact whatsoever on our calculation. The only thing we care about is the mass of water and the change in temperature. So, our mass of water, remember it's 1 gram per milliliter, 50 milliliters makes 50 grams. The temperature change is quite small, 0.33 degrees Celsius. So then, with our handy-dandy equation in place, we have 50 grams of water, the heat capacity of water, times only 0.33 degrees Celsius. 69 joules by my count have been transferred from the gold to the water. So we can actually do something interesting once we are willing to accept the first law of thermodynamics. Remember that we just calculated that the amount of energy that was given to the water from the gold was 69 joules. Now imagine for a second that we didn't know the heat capacity of gold. So if we want to know the specific heat capacity of gold, all we'd have to do is turn the question around and say, okay, well, all the energy that was given to water had to have come from the gold itself. So if we wanted to calculate the specific heat capacity of gold, we'd simply have to weigh the sample. In this case, it was 6.77 grams, and realize that the final temperature of the gold had to be the same as the water in the calorimeter. So now we've got a mass of gold of 6.77 grams. We know the energy that the gold gave up was 69 joules. We know our initial temperature of the gold was 100 degrees when we put it into the calorimeter, and that its final temperature was 21.33 degrees Celsius. So our change in temperature is negative 78.67 degrees C. We have Q, 69 joules, and we have the mass. So we can just simply rearrange this and solve for C. And I'd invite you to do that yourself and check the answer against Google to be sure that you've got the right calculation. Okay, and we can do similar things where instead of the heat source being an object that we place into the calorimeter, we can react two things together, measure the temperature before and after reacting them, and assuming that we've got an isolated system, the only place that change in temperature can come from is from the chemical reaction. So in this case, we have a 50 gram sample of 1 molar hydrochloric acid and 50 mils of 1 molar sodium hydroxide. And we mix them together, and the temperature moves from 25 degrees C to 31.9 degrees C. And so this is a very typical question you could be asked. Determine the quantity of thermal energy transferred by the reaction to the water. So this calculation is really no different than the one for the gold sample being placed inside. The only difference is that the energy came from the reaction. So the temperature change, it went up 6.9 degrees C. The heat capacity is simply the density of water times 100 mils. Remember, we mixed two 50 mil samples together. And we get 2.9 kilojoules was given off by the reaction. The fact that the temperature went up indicates that this is an exothermic reaction. So, hopefully this gives you a good starting point to be able to do the calorimetry virtual experiment online. So here's a hyperlink to it here. Please go ahead and work on that activity. You should find it fairly interesting. And keep in mind the fundamental pieces of what we've talked about today. Energy is the capacity to do work. Heat is energy transferred to and from the surroundings. The specific heat capacity is the energy required to change the temperature of a 1 gram sample 1 degree. So go ahead and finish up that activity and work on the worksheet, and have a great night.